So next, we're going to watch another clip that I think is very reflective of his physical attitude, his attitude towards physics, and again, the pragmatism is going to come out here.
Interesting. So if you'll permit me, I'm going to state the law of gravitation in 3 different ways, all of which are exactly equivalent, it turns out. But they sound completely different. 1, there's a forces between the objects as described before, and each object, when it sees the force on it, accelerates or changes its motion at a certain amount per second, as I've described before. The regular way, I call it Newton's law. Now there's a completely different way. That law says that the force depends on something at a finite distance away. See, it has what we call non-local quality. The force on this depends on where that one is over there. Now, you may not like the idea of action at a distance, but it can know what's going on over there. So then there's another way of stating the laws, which are very strange, and it's called the field way of representing the laws. And it's so very hard to explain, but I just want to give you some rough idea of what it's like. And it says different things, completely different things. That there's a number at every point in space. I know it's a number. It's not a mechanism. It's the trouble with this whole physics, that it must be mathematical this way. There's a number at every point in space. Here's a number, and so on. And the number's changing. It changes, rather, when you go from place to place. If an object is placed at one of these points, at somewhere in space, the force on it is in a direction in which that number, I'll call it the name it's given, called a potential, is in a direction in which that potential changes as quick as it can. And the force is proportional to how fast it changes as you move. Newton's laws tell what happened at one time in terms of what happens in another instant. It gives from instant to instant how to work it out. But in space, it leaps from place to place. But this thing is both local in time and also local in space, because it depends only on what's in the neighborhood. And there's another way of representing. That's another way. Now, there's a completely different way. See, there's a difference in the philosophy, in the qualitative ideas involved. You don't like action at a distance, you can get away without it. Now I'll show you one which is philosophically the exact opposite, in which there's no discussion at all about how the thing works its way from place to place, in which the whole thing is an overall statement, as goes as follows. When you have other particles around and you want to know how this one moves from one place to another, you do it as follows. You calculate a certain quantity, you invent a possible motion that gets from one given place to some other place that you're interested in a given amount of time. Say it wants to go from here to here in an hour, and you want to know by what route it can get from there to there in an hour, by what curve. So what you do is you calculate a quantity guessing the curve. If you try this curve, you calculate a certain number for this quantity. I don't want to just say what the quantity is, but for those who have heard of these terms, this quantity on this route is the average of the difference between the kinetic and potential energy. Now, if you calculate this quantity for this route and for another route, you'll get, of course, different numbers for the answer. But there's one route which gives the least possible number for that, and that's the route that the particle takes. Now we're describing the actual motion, the ellipse, by saying something about the whole curve. We have lost the idea of causality, that the particle's here, it sees the pull, it moves to here, it goes. Instead of that, in some grand fashion, it smells all the curves around here, all the possibilities, and decides which one to take. But this is an example of the wide range of beautiful ways of describing nature, and that when people talk that nature must have causality, well, you could talk about it this way. Nature must be stated in terms of a minimum principle. Well, you can talk about it this way. Nature must have a local field. You can do that, and so on. And the question is, which one is right? Now, if these various alternatives are mathematically not exactly equivalent, and if for certain ones there will be different consequences than for others, then that's perfectly all right then, because we have to only to do the experiments to find out which way nature actually chooses to do it. Mostly people come along and they argue philosophically they like this one better than that one, but we have learned from much experience that all intuitions about what nature's going to do philosophically fail. It never works. One just has to work out all the possibilities and just try all the alternatives.
Alrighty, so that's Feynman's view on different formulations of the same physical law. What I found interesting about this is that he's saying, first of all, what I would call a physical theory, he calls a philosophy. So already he's on the view that, like, once you start talking about what I was saying before, entities acting on one another, once you start talking about that, says Feynman, you're now leaving the realm of physics. And this has been something that, this almost made me quit physics, by the way, because I hated the idea of just doing math to, like, make predictions and that's it. I wanted to understand what was actually going on. And implicitly for years, and then explicitly once I got to graduate school, implicitly for years in undergrad, I was told, like, well, that doesn't matter. Then explicitly, once I started wising up and saying, well, I want to know what's actually going on, they started looking at me like, well, that's not what this is about, James. So, comments on this, Aviram?
Yes. I think that the history of physics suggests an interesting example. If I'm not mistaken, in the 17th century, Fermat said, or rather noticed, that beams of light go through the path of the shortest path possible. I think it's the least path, optical least path. And
that takes the least amount of time, I think.
Yeah, and this was a rather obscure property, because presumably it would cause you to think that light somehow knows which path is the shortest. But then when
I remember not even liking that when I was a little kid. I finally know what I didn't like about that now.
Yeah. So when Maxwell's theory was derived, and people understood how to interpret light beams within the structure of the fields that Maxwell was describing in his equations, then they were also able to derive the shortest path property that Fermat's principle is talking about. And so, in a sense, what Feynman says is true, but I'm not sure whether the conclusion follows that you have to be totally unprincipled and pragmatic about the different formalisms. In a sense, eventually you do want to find a hierarchy and explain the more fundamental properties by means of the more fundamental properties, the ones that are higher up, the ones that are consequential of the more fundamental properties.
Yeah, instead of just whichever one works, that's what we use. Now, you might be thinking that we're making Feynman's point for him. We have this bias towards, causal theories that act at specific, with entities acting at specific times, and we haven't and how do you know that's actually how it works? Well, here's why: is because reality consists of entities. And the reason things happen is because entities are acting on one another. There aren't any sort of abstract laws that live in reality. Think about that. That would be like we live in a computer simulation and there's like a source code to the universe that the entities are following. No, entities don't follow like abstract laws written in the sky by God or Morpheus or whoever. Like, entities have identities, entities have natures, and they act and relate to one another in accordance with those natures. So, and here's how that specifically applies to a principle of least action. So a principle of least action, it's this overall principle that the motion of some object has to follow. Or in the case of light, it's the fact that the path it ends up taking always ends up being the path that causes it to minimize its flight time, basically. So that's great. I think, again, that's great, but that doesn't get to the essence of the physical law. So let's think of gravitation. In the case of gravitation, it's like whatever is actually the underlying identity of the gravitational force and how it is propagated, it cannot be action at a distance. First of all, it can't be, I don't think action at a distance is ruled out, but based on what we see, gravity, spreads out spherically, and it follows an inverse square law, which means it's spreading out spherically. It spreads out at a finite speed. It's not non-local. It's local. It spreads out and acts at particular locations. Okay, now secondly, how do we know it's not a least action principle? Well, a least action principle involves sort of this summary of all of the actions, but entities act in accordance with their nature at the time that they have it. If there was some kind of least action principle, it would mean that there would have to be some kind of like entity sort of like, conditioning the way that the particle moved at all given times. Well, that does exist. It's called gravity, and it's acting at each particular location during the path. And you'll notice that Feynman even has to rely on the causal view in order to describe what a principle of least action does. He says that it's somehow, the principle of least action somehow, he doesn't even know how. I would like to know how, by the way. I don't know either, but I at least want to find out. How does it... Anyway, he says the principle of least action sniffs out the forces at each given location and then provides like a summary view. Yeah, exactly. That's what it does, which means that the forces, specifically the local forces, which means that the fields are what's actually fundamental. Now, you might be thinking, like, why does this matter? Why does it matter? Like, these are just different formulations. Yeah, technically, maybe it's entities acting at certain locations, but, like, isn't that just, like, abstract stuff that doesn't really matter that much? No, it matters a great deal. Let me give you an example. So, back during roughly the time of Galileo, there was another physicist named Evangelista Torricelli. I think it was a little after Galileo, actually. But anyway, Torricelli was trying to figure out how vacuum pumps worked. He was pumping air out of a certain container, and when he did that, he found that the vacuum, once you pump the air out, was able to suck water up through a straw or through a pipe. So basically, imagine when you sip on soda through a straw, you're just you're sucking the air out of the straw, and that causes the soda to rise. So Torricelli was trying to figure out how that worked, only it wasn't involving soda. Now, other people's way of thinking about this is they said, it must be some kind of general law that nature abhors a vacuum. So you suck the air out of the straw, and nature abhors a vacuum, so the soda rises to fill the straw. And Torricelli wasn't convinced by that. Instead, what he said is, wait a second. And he said, wait a second, vacuums aren't an entity. You can't talk about the vacuum sucking stuff up, because a vacuum isn't a thing. And this allowed him to realize that when you suck the air out of the straw, you're not sucking the soda up. Instead, what you're doing is you're removing air from the straw, which removes an impediment. What does it remove an impediment on? It removes the impediment on the atmosphere. The atmosphere is pressing down on your soda, and that the atmosphere pressing down on your soda, once you remove the air from the straw, it pushes the soda up into your mouth. So it's not that you're sucking the soda up, it's that you're just removing the impediment for the atmosphere to push the soda into your mouth. And Torricelli couldn't have discovered this without the attitude that these physical laws function by entities acting. He wasn't satisfied with, the general law, nature abhors a vacuum. No. The entity, the atmosphere, pushes the other entity, the soda, up into your mouth. Comments on this, Aviram?
Do you like the way I explain things? Are you tired of training yourself like a monkey to repeat steps on a test without understanding anything? Well, then you're in luck. Just go to inductica.org/contact and you can book a coaching session with yours truly. I cover all levels of math and physics, including very difficult subjects such as quantum mechanics. All right, back to the video.
I like this example a lot. I would just be interested in looking up the history and seeing whether it's possible to make the fear of vacuum more rational. Suppose that someone say, no, it's not really that nature knows that a vacuum is going to form there, and so it rushes to close the gap. They might say there is some sort of force of cohesion, some sort of stickiness that makes things not split apart. But prima facie, I think that you made a very interesting connection. Yes, I mean, the idea that nature feels a vacuum does really sound like nature is lazy and he wants to take the path of least resistance. That's unsatisfying. It's a kind of metaphor. It's a kind of image to interpret a certain principle, whether mathematical or qualitative. But eventually, you would have to cash it in with a definite kind of explanation.
Yeah, and as long as we think in that metaphor, any of the inferences that will come from thinking in the literal facts of the matter will be hidden to us.
I think that Feynman is noting a legitimate issue here. It is a good thing to have, as a physicist, under your belt, several formalisms or several tools in order to deal with theoretical problems when you want to explain a certain phenomena, for example, or investigate a certain poorly understood one.
This should not be taken as a denouncement of the Lagrangian mechanics or of any kind of theory that is a principle of least action or anything like that. Only to say that we need to be very cognizant of what's physically happening, and a certain theory, and one theory might be very useful, but it doesn't necessarily reflect the physical reality directly. And if it does so only by sniffing out all of those specific physical actions and summarizing them somehow.
Yes, and so one metaphor that I have to think about this is to compare it to the use of different measures of units of measurement. So in atomic physics, people use angstroms, which is a very, very minute measure of length. But in astronomy, they use the astronomical unit, the AU. And you can see there why different tools, let me hide the glow here. You can see there why different tools match different contexts. And my suspicion is that what's going on with the principle of least action is that it's not entirely understood what's the context in which that kind of principle is most useful. But probably what's happening is that least action is the form of the laws of nature which is best suitable for certain kinds of tasks. And we have to ask why. And so in the case of units, you prefer a certain unit because it makes the numbers that you are working with smaller than they would otherwise be. And so there is here an issue of tailoring the right tool to the right problem, but this should not imply a certain disinterest in the right hierarchy of physical principles.
Yes.